FasterTransformer is an open-source library developed by Nvidia designed to speed up and optimize transformer model inference. It's particularly helpful for large natural language processing, NLP models like BERT, GPT-2, and T5, especially when these models are deployed in real-time applications such as translation, summarization, and text generation. The main goal of FasterTransformer is to reduce inference latency and increase throughput, meaning it makes the process of getting predictions from these models faster and more efficient. Let's explore it in 4 parts. The FasterTransformer architecture. How does FasterTransformer's layer fusion technique reduce memory usage? The multi-head attention acceleration technique in FasterTransformer. GEMM kernel auto-tuning and how does it improve performance? Now, let's explore how FasterTransformer architecture achieves this. The first, key architectural features. 1. GPU optimization. FasterTransformer leverages Nvidia GPU through custom CUDA kernels. CUDA is a programming model that allows software to run on Nvidia GPU, which are highly efficient for tasks like matrix multiplications, operations that transformer models rely heavily on. This means computations that were traditionally done on the CPU are now performed on the GPU, speeding up processing time significantly. FasterTransformer supports several Nvidia GPU architectures, like Volta, Turing, and Ampere, so it works across a range of devices. 2. Efficient kernel implementations. The library includes optimized implementations of core operations in transformers, such as softmax, a function used in attention mechanisms to normalize values. Attention mechanisms. The heart of transformer models, which allows the model to focus on different parts of the input. Feed-forward networks. After attention, these networks process the output. These optimizations make the core calculations in transformer models much faster and more efficient. 3. Dynamic sequence lengths. FasterTransformer can handle dynamic sequence lengths, which means it doesn't need to pad the input sequences to a fixed length. This saves time and memory, as padding can often be wasteful and slow down computation. 4. Layer fusion. Layer fusion is a technique where multiple operations, or layers, are combined into a single computational step. This reduces the number of times data has to be moved between the GPU global memory and shared memory. This optimization speeds up computations and reduces memory usage. For example, operations like adding a bias to the output and applying layer normalization can be combined to improve efficiency. 5. Multi-head attention acceleration. The multi-head attention mechanism is a critical and computationally expensive part of transformers. FasterTransformer optimizes this by using a key value cache. This cache stores the results of previous attention operations, which helps to avoid recalculating the same values repeatedly. Additionally, fused kernels are used to reduce memory transfer sizes and speed up the process. 6. GEMM kernel auto-tuning. General matrix multiply, GEMM operations are central to deep learning tasks, and FasterTransformer improves their performance with auto-tuning. This means that the system adjusts the kernel, the function that handles the computation, based on the size and shape of the matrices being multiplied. This dynamic optimization ensures that GEMM operations are always as efficient as possible. 7. Lower precision computation. To boost performance even further, FasterTransformer uses 16-bit floating point numbers instead of the usual 32-bit. This reduces memory usage and speeds up computations without losing too much precision. For most NLP tasks, this trade-off is negligible, but provides a significant performance improvement. The second, model parallelism techniques. FasterTransformer also employs 2 types of parallelism to handle large models efficiently. 1. Tensor parallelism. This splits the model's tensors, the data that flows through the model, across multiple GPU. For example, the weights in attention blocks or feed-forward networks are divided into smaller pieces, which are processed simultaneously on different GPU. This allows the model to scale across multiple devices. 2. Pipeline parallelism. Instead of processing the entire model at once, this technique breaks the model into segments. Each segment is processed by a different GPU, and the layers can be computed concurrently across devices. This also helps hide communication latencies, improving overall performance. The third, integration with frameworks. FasterTransformer provides API that are compatible with popular machine learning frameworks like TensorFlow and PyTorch. This means that developers can integrate it into their existing workflows with minimal effort. If you're already using these frameworks, it's easy to take advantage of FasterTransformer's optimizations. In summary, FasterTransformer is a powerful tool for optimizing transformer models, especially for large-scale NLP tasks. By making use of GPU optimizations, advanced memory management, dynamic sequence handling, and techniques like model parallelism, it significantly speeds up inference tasks. Whether you're working with translation, summarization, or text generation, FasterTransformer can help you get faster results without sacrificing too much in terms of accuracy. Now let's break down how FasterTransformer uses layer fusion to reduce memory usage and improve performance. Layer fusion is a technique that combines multiple layers of a transformer model into a single computational operation. This offers several advantages in terms of memory efficiency, and here's how it works. The first, reduction of intermediate data storage. In traditional transformer models, each layer produces an output that becomes the input for the next layer. This means that the model needs to store the outputs from each layer temporarily. With layer fusion, FasterTransformer combines multiple layers into one operation. By doing so, it reduces the need to store these intermediate results, which leads to a significant reduction in memory usage. This allows the system to handle larger models and datasets without running into memory limitations. The second, decreased data transfer requirements. In standard models, data often needs to be transferred between the GPU global memory and shared memory during processing. These transfers can be time-consuming and inefficient. Layer fusion helps reduce the frequency of these data transfers. By fusing layers together, FasterTransformer minimizes the number of times data has to be moved between memory spaces. This not only speeds up the computation, but also reduces the memory overhead associated with these transfers, which further improves performance. The third, increased computational efficiency. When layers are fused, multiple operations are performed within a single kernel call. A kernel is essentially a function that runs on the GPU, and when you combine several operations into one, you maximize the computation done with each memory access. This results in more efficient use of the GPU resources, as fewer features need to be stored at any given time, leading to a reduction in memory usage during inference. The fourth, memory buffer reuse. Another key strategy is memory buffer reuse. Instead of allocating separate memory for each layer's outputs, FasterTransformer reuses the same memory buffer for different layers. This is especially useful in large models, where the number of layers can be quite substantial. By reusing memory buffers across layers, FasterTransformer saves a significant amount of memory, allowing it to scale more effectively. The fifth, optimized execution schedules. FasterTransformer optimizes the execution schedules for layer-fused operations. These schedules take into account the size and shape of the input data, ensuring that only the necessary data is kept in memory at any given time. By adapting the execution to the characteristics of the input, FasterTransformer can further reduce memory usage and make the process more efficient. To summarize, layer fusion in FasterTransformer helps reduce memory usage in several ways. By minimizing the need to store intermediate data, reducing the frequency of data transfers, improving computational efficiency, reusing memory buffers, and optimizing execution schedules. These strategies work together to enable FasterTransformer to handle large transformer models more effectively while maintaining high performance. This is especially important in resource-constrained environments where memory and computational efficiency are critical. Now let's break down FasterTransformer's approach to optimizing multi-head attention, a key component of transformer models, and how it improves computational efficiency. The first, optimizing attention computations. In transformer models, the multi-head attention mechanism allows the model to focus on different parts of the input sequence at the same time, helping it capture relationships and nuances in the data. However, this can be computationally expensive because of the large number of matrix multiplications and memory accesses involved. FasterTransformer addresses this by optimizing these computations. This makes the process faster without sacrificing the model's predictive accuracy. It's like streamlining the work so that the model can focus on the important tasks more efficiently. The second, key value caching. Another key optimization is the use of a key value cache. During inference, FasterTransformer stores previously computed key and value tensors in this cache. This means that when the model processes new tokens, it doesn't need to recompute everything from scratch. Instead, it reuses the previously computed values. This is particularly helpful for tasks like incremental text generation, where each new token depends on the previous one. By reducing redundant computations, the model runs much faster. The third, fused kernel operations. FasterTransformer also uses fused kernel operations for the multi-head attention process. Normally, multi-head attention involves several steps: calculating attention scores, applying softmax, and then performing other operations. Each of these steps usually requires its own kernel, but FasterTransformer fuses them into a single operation. This reduces the overhead of managing multiple kernels and cuts down on memory transfer times, making the whole process more efficient. The fourth, handling dynamic sequence lengths. FasterTransformer also excels at handling sequences of varying lengths. In traditional transformer models, padding is often used to make all sequences the same length, which can increase memory usage and slow down computations. But FasterTransformer's approach doesn't require padding for sequences of different lengths. It adapts to the actual lengths of the sequences, which improves both the speed and efficiency of memory usage. The fifth, integration with other optimizations. FasterTransformer's multi-head attention acceleration works alongside other optimizations. For example, layer fusion merges multiple layers into one computational step, and GEMM kernel autotuning optimizes matrix multiplication operations. These techniques, when combined, create an even more efficient pipeline for inference. The result is faster performance and reduced resource usage while still maintaining the accuracy of the model's predictions. To sum up, FasterTransformer's multi-head attention acceleration is an essential part of making transformer models faster and more efficient. By optimizing attention computations through key value caching, fused kernel operations, and dynamic sequence handling, it significantly improves inference speed without compromising on model quality. And when combined with other optimizations, FasterTransformer delivers an even more powerful solution for transformer-based tasks. Let's talk about GEMM kernel autotuning, which is an important optimization technique used in FasterTransformer to improve the performance of matrix multiplication operations. These operations, which are at the heart of many deep learning models, can be quite computationally expensive. GEMM kernel autotuning makes sure that these operations run as efficiently as possible. What is GEMM kernel autotuning? GEMM kernel autotuning is the process of automatically adjusting the parameters of the GEMM, general matrix multiply operation, to get the best possible performance based on the specific matrix sizes and shapes involved in the computation. This ensures that each GEMM operation is optimized for the given workload, making it more efficient. Here's what goes into this process. 1. Parameter optimization. This step involves finding and adjusting the right parameters that control how the GEMM operation runs. These parameters could include things like thread block sizes and memory access patterns. The goal is to identify the best settings to run GEMM on a given matrix and hardware configuration. 2. Performance evaluation. Once different parameter settings are identified, the next step is to run multiple versions of the GEMM kernel. By testing how each one performs, the system can determine the most effective setup for the given matrix dimensions. Now let's look at how GEMM kernel autotuning benefits FasterTransformer. 1. Optimized performance for varying matrix sizes. The size of the matrices involved in matrix multiplication can greatly influence the performance of GEMM operations. With autotuning, FasterTransformer can adjust the GEMM kernel for the specific matrix dimensions it's working with, ensuring optimal performance no matter the input size. 2. Increased computational throughput. Autotuning allows FasterTransformer to make the best use of the GPU by running the GEMM operations as efficiently as possible. This means that more operations can be processed in a shorter amount of time, leading to higher throughput. 3. Adaptation to hardware variability. Not all GPU are the same. Different GPU architectures, like Volta, Turing, or Ampere, may have different configurations that work best for GEMM operations. Auto-tuning allows FasterTransformer to adjust to these hardware differences, ensuring consistent high performance across different types of GPU. 4. Reduction in latency. By optimizing GEMM operations, auto-tuning helps reduce the latency during inference. This is especially crucial for real-time applications, such as chatbots or live translation services, where quick responses are key. 5. Dynamic adjustment. Auto-tuning is not a one-time setup. It can dynamically adjust the parameters while the model is running, based on the workload or the characteristics of the input. This means that FasterTransformer can continuously adapt to changing conditions without requiring manual intervention. 6. Improved resource utilization. When the GEMM kernels are efficiently tuned, FasterTransformer can use GPU resources, like memory bandwidth and computational cores, more effectively. This results in less wasted computational power and better overall processing. In summary, GEMM kernel auto-tuning is a key feature in FasterTransformer that helps optimize matrix multiplication operations. By automatically adjusting kernel parameters based on matrix sizes and GPU architecture, it boosts performance, increases throughput, reduces latency, and improves resource utilization. This makes FasterTransformer more efficient when running inference tasks on Nvidia GPU, especially for large-scale transformer models.